This videotape deals with graphing parabolas. The graph of an equation, of the form y equals ax squared plus bx plus c, where a, b, and c are constants, with a not equal to 0, is called a parabola. And the graph of an equation of this form, y equals ax squared plus bx plus c, where a, b, and c are constants, with a not equal to 0, is called a parabola. In this tape, we're going to learn how to graph parabolas. We're going to learn that by plotting a few important points, we can get enough information to get a good picture of this curve, rather than just, say, going haphazardly into a table of values. Okay? You can say, with, say, 3 points or so, get a very good picture of what's going on here, get an accurate sketch of the parabola. And this videotape is going to teach us how to do that. Now, the key to graphing parabolas of this form is to get the intercepts, the x and the y intercepts of this curve. You'll remember that the x-intercept of a curve is the x-coordinate of the point where the curve crosses. The x-axis, the y-intercept of a curve, is the y-coordinate of the point where the curve crosses the y-axis. Now, to find the y-intercept, okay, to find the y-intercept, we let x equal 0. And we see that y would be equal to a times 0 squared plus b times 0 plus c, or y equals c. So the y-intercept is c for this curve. To find the x-intercept, the place where the curve crosses the x-axis, when it crosses the x-axis, the y-coordinate naturally would be 0. So we're going to set y equal to 0 and try to solve for x. If we set y equal to 0, we will get ax squared plus bx plus c equals 0. We have a quadratic equation in the variable x. Now, we know that an equation of this form has at most 2 real roots. It might have 2 real roots, it might have 1 real root, it might have no real roots. There are 3 possibilities here. And depending on how many real roots this equation has, that determines how many x-intercepts the parabola has. So we have 3 possibilities. Okay, would have, so this is the x-axis in each case, and this is the y-axis. For the sake of argument, let's assume these parabolas are all opening upwards. Okay, they can open upwards or downwards, these particular types of parabolas. Now, it could have a situation like this, where the parabola has 2 x-intercept, crosses the x-axis twice. Okay, when you try to find the x-intercept, when you set y equal to 0, this quadratic equation would have 2 real roots, giving you these 2 x-intercepts. You might have a situation like this, where the turning point of the parabola, in this case the lowest point, or the vertex of the parabola, actually lies on the x-axis. It is the x-intercept. In this case, there would be only 1 x-intercept. Or you might have a case where the turning point of the parabola is above the x-axis, and the parabola is opening upwards, so there are no x-intercepts. So here we see illustrated the possibility of 2 x-intercept, 1 x-intercept, no x-intercepts for a parabola of this form. Okay, let's actually get into some specific examples. Let's say we would like to sketch the parabola y equals minus x squared plus 2x plus 15. Okay, to get the y-intercept, we set x equal to 0 and we see when x equals 0, y is equal to plus 15. So the y-intercept is 15. To find the x-intercept, we set y equal to 0. And if y equals 0, we get minus x squared plus 2x plus 15 equals 0. We have a quadratic equation in x. I would like to solve for x. Okay, I find it convenient in such a case to, if I would like to try to factor this, and I find it convenient to try to start with the lead coefficient positive rather than negative. So I'm going to factor out a minus 1 here, leaving with x squared minus 2x minus 15 equals 0. Or you could divide both sides by minus 1 and just get x squared minus 2x minus 15 equals 0. And now, this is fairly simple to factor. We're looking for two numbers which multiply to minus 15 and add to minus 2, and they are, of course, minus 5 and plus 3. Checking this by FOIL, we'd have x squared plus 3x minus 5x. That's minus 2x minus 15, giving us now x equals 5, x equals minus 3, two x-intercepts. Okay, let's look at what we have so far. Let's make a sketch. We have a y-intercept at 0, 15. It crosses the y-axis. So here is 0, 15. We have x-intercepts at 5 and minus 3. It crosses the x-axis at 1, 2, 3, 4, 5. X equals plus 5, and x equals minus 3. Okay. Now, we could really use a little bit more information, okay, to sketch the graph of this parabola. We have the feeling it's probably going to be going down like this, but we're not exactly sure where the highest point on the parabola is. Where is the turning point or the vertex? Okay, that would be a very useful point to have. If a parabola is of the form y equals ax squared plus bx plus c, then by using the idea of completing the square, it is possible to show that the x-coordinate of the turning point, the x-coordinate of the vertex, is given by the following formula. The x-coordinate of the vertex or turning point of the parabola is given by x equals minus b over 2a. Okay, as I said, you can verify this by using the idea of completing the square. Okay, now this would be a very useful point to have. If the x-coordinate is given by this, we could then find the y-coordinate by substitution. In our problem, we are working with the parabola y equals minus x squared plus 2x plus 15. So a is equal to minus 1, b equals 2, c equals 15. A x squared plus bx plus c. So the x-coordinate of the vertex is given by minus b over 2a, or minus 2 over 2 times minus 1, minus b over 2a, minus 2 over 2 times minus 1. That's minus 2 over minus 2, or plus 1. Okay? And if x equals 1, you can figure out the y value that goes with that. If x equals 1, substituting into the original equation, you get y equals minus 1 plus 2 plus 15, minus 1 plus 2 plus 15, or 17 minus 1, y equals 16. So we now know that 116 is a point on the parabola, and furthermore, it is the turning point, in this case, the highest point on the parabola. Okay, so we can now sketch our parabola. Without that, we might have drawn the parabola slightly off, we might have thought, say, mistakenly, that this was the highest point. So it's a very useful point to have. If you have the turning point of the parabola, okay, and then a few intercepts, you really have enough information to sketch the graph of the parabola. For our next example, I would like to sketch the graph of this parabola, y equals x squared minus 2x minus 10. Okay, the y-intercept found by setting x equal to 0 when x equals 0, y is equal to minus 10. To get the x-intercept, or intercepts, depending on what we get, we set y equal to 0, and we get that x squared minus 2x minus 10 equals 0. Now, unlike the preceding problem, this particular quadratic equation cannot be solved by factoring. We cannot find two integers that multiply to minus 10 and add to minus 2. So we're going to have to solve this one using the quadratic formula. Matching this up to ax squared plus bx plus c equals 0, we see that a equals 1, b equals minus 2, c equals minus 10. And the quadratic formula tells us that x equals minus b plus and minus the square root of b squared minus 4ac over 2a are the roots of this equation. And if we can find these real numbers, then those would be the x-intercepts of the parabola. So let's substitute in and see what we get. X equals minus b minus a minus 2 plus and minus the square root of b squared, which is minus 2 squared, minus 4, a, which is 1, c, which is minus 10, all over 2a. Okay, we get minus a minus 2, that's plus 2, plus and minus the square root of minus 2 squared, that's 4, minus 4 times minus 10, that's plus 40, all over 2, which gives us 2 plus and minus the square root of 44 over 2. We can do a little simplification on that. We see x equals 2 plus and minus the square root of 44 over 2. This is 2 plus and minus. Now 44 is 4 times 11. So we get the square root of 4 times 11 over 2, which gives us 2 plus and minus. Now this is the square root of 4 times the square root of 11. Okay, so this gives us 2 plus and minus 2, the square root of 11 over 2. We're almost there. We can further simplify by factoring out a 2 on top. 2 times 1 plus and minus the square root of 11 all over 2. This is 2 plus or minus 2, the square root of 11, which is what we have here. If you were to distribute the 2 through the parentheses, you can divide numerator and denominator by 2, so you get x equals 1 plus or minus the square root of 11. So this gives us two possible x intercepts here. X equals 1 plus the square root of 11, and x equals 1 minus the square root of 11. Now the square root of 11 is about 3.3. So we get it's approximately 1 plus 3.3, or approximately equal 4.3 for one of the intercepts, and for the other one, 1 minus 3.3 approximately, or approximately minus 2.3 for that x-intercept. Okay, so we have the y-intercept, which is minus 10, and we now have two x-intercepts for this parabola. Okay, it would also be useful to know the turning point, the x-coordinate of the vertex. Remember, in this case, the x-coordinate is given by minus b over 2a, and the y coordinate is found by substituting into the original equation. Y equals x squared minus 2x minus 10. A equals 1 here, and b is equal to minus 2. Okay? It's ax squared plus bx plus c. So we get that the x-coordinate of the vertex is minus a minus 2 minus b over 2 times a. Minus a minus 2, that's 2 over 2, which is 1. Okay, it's coincidental that this came out to be 1, and the last example, the x-coordinate of the vertex was also 1. Okay, just the way it happened to work out. Now here, if x equals 1, to figure out the y value, we plug into the original equation here. Y equals 1 squared minus 2 times 1 minus 10, 1 minus 12, or minus 11 for the y coordinate of the vertex. So let's make a sketch and see what we have. We have a vertex at 1 minus 11. We have the y-intercept is at minus 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0 minus 10 is the y-intercept. 1 minus 11 is the vertex, the turning point. The x-intercepts were about 4.3, right around there, and minus 2.3, around there. Okay, so we have a pretty good idea of what's going on here. I wish it would look a little smoother here. Of course, is a smooth turning around here at the vertex. An interesting thing here, in this particular problem, the vertex, which was a turning point on the parabola, was the lowest point on the parabola, whereas in the preceding problem that we worked out, the vertex was the highest point on the parabola. Okay, this parabola is opening upwards. The other parabola that we just worked out was opening downwards. There is a clue, okay, before you sketch the parabola as to which way it's going to be opening up, and the clue is provided by the value of a in the parabola. Okay, in this case, y equals x squared minus 2x minus 10. A is the coefficient of the quadratic term here. It's 1 in this case. It's positive. If a is positive, the parabola is opening upwards like this. The vertex will be the lowest point on the parabola. Okay, and when you get a moment, look back to the first example. In that example, a was negative. Okay, and the parabola was opening downwards, like so, and the turning point was the highest point on the parabola. When a is negative, the parabola opens downwards. When a is positive, as in this case, the parabola is opening upwards. Okay, this time I'd like to sketch the graph of y equals x squared plus 4x plus 6. We recognize this once again as a parabola. It's in the form y equals ax squared plus bx plus c. To get the y-intercept, we set x equal to 0, and when x equals 0, y is equal to 6. To get the x-intercept, we set y equal to 0, and we get the quadratic equation x squared plus 4x plus 6 to solve. In this problem, a is equal to 1, b is equal to 4, and c is equal to 6. We're matching this to ax squared plus bx plus c equals 0. Once again, this problem cannot be solved by factoring. Okay, we cannot find two integers that multiply to 6 and add 2 plus 4. We're going to solve it by using the quadratic formula. X is equal to minus b plus and minus the square root of b squared minus 4ac over 2a. We get, by substitution, minus 4 minus b plus or minus the square root of b squared, that's 4 squared, minus 4 times a, which is 1, times c, which is 6, all over 2 times a, 2 times 1. Okay, so we get minus 4 plus or minus. Now, look at this. We get 16 minus 24, or minus 8 under the radical. Okay, now we know that there is no real number. Okay, the square root of minus 8 is not a real number. There is no real number which, when squared, will give you minus 8. Okay, a positive number times itself is positive, a negative number times itself is negative, a negative number times itself is positive, and 0 times itself is 0. Okay, so there's no, the square root of minus 8 is not a real number. Now, this means that there are no real solutions to this quadratic equation. This corresponds to the case where there are no x-intercepts. Okay, we set y equal to 0. We try to solve for x, meaning we like a real value for x. I can only plot real numbers on my graph. Okay, this is not a real number. So there are no x-intercepts in this problem. There is a y-intercept, but no x-intercepts. Furthermore, since a equals 1, we know that this parabola is opening upwards. Okay, let us get the coordinates of the vertex of the parabola. Okay. The x-coordinate is given by minus b over 2a, and the y-coordinate is found by substituting that into the equation. Y equals x squared plus 4x plus 6. So, in this problem, we know b is equal to 4. So we get minus 4 over 2 times a. A is equal to 1, and we get minus 2 for the x-coordinate of the vertex. The y-coordinate is found by substituting into the original equation. We get minus 2 squared plus 4 times minus 2 plus 6. Okay, this would give us 4 minus 8 plus 6. That's 10 minus 8, or 2. So the vertex has coordinates minus 2 comma plus 2. Okay, let's see what we have so far. Now, in all the other problems, just the intercepts in the vertex was enough to sketch the parabola. Here, however, we have the coordinates of the vertex. It occurs at minus 2, 2. We know the y-intercept is 6. Okay. We do not have any x-intercepts on the parabola. Okay. We could sort of say, look, the parabola has to be going like this. It can't be going like this, because that would mean it has x-intercepts. A is positive. We know the parabola is opening upwards. The vertex is the lowest point on the parabola. We could sort of sketch it in like this, since we do know this is the lowest point, but it would be nice to have another point on the parabola to help us in our sketch. Okay, whatever you do, don't connect this and make it look like a straight line. Okay, you know it's a parabola. Okay, you know the y-intercept, you know there are no x-intercepts. This is the vertex, the turning point. It's going to turn around there. Okay, now we'd like to get another point on this parabola. Y equals x squared plus 4x plus 6. Okay, one nice way to find another point would be to let y equal c. In this case, y equals 6, and solve for x. It's a particularly easy quadratic equation results, and you can get a very nice point which is symmetrically located on the other side, okay, of this y-intercept from the vertex. It's a helpful point to get. Let's set y equal to 6. In other words, whatever the constant is here, c. If y is equal to 6, we get 6 is equal to x squared plus 4x plus 6. Subtracting 6 from both sides, we get 0 equals x squared plus 4x. This is a very easy quadratic equation to solve because we don't have a constant term. we can just factor out the x. We get x times x plus 4 equals 0, so we get x equals 0, x plus 4 equals 0, x equals 0, x equals minus 4. These are the two x values that go with y equals 6. Remember, we let y equal 6, we solve for x. So we have x equals 0, y equals 6 is 1 point, x equals minus 4, y equals 6 is another point. Now 0, 6, we've already plotted. That was the y-intercept. Okay, but the other point that's useful in sketching the parabola is x equals minus 4, y equals 6. Okay, here we certainly have the ability to sketch the parabola very nicely. We have this third point, which is situated over here on the other side of the vertex. If you choose, by the way, not to do it this way, and you wanted to just plot some more points, you could have just substitute different values for x, okay, and find y. Of course, make sure you are finding x values to the left of the plugging in x values to the left, or less than the x coordinate of the vertex here. Okay, we already know what's going on here. We don't want it to look like a straight line, so make sure you get some points on the other side of the vertex. So this is a very neat way for getting another point on the other side of the vertex. Y equals x squared plus 6x plus 9. Once again, a parabola of the form y equals ax squared plus bx plus c. And we get the y-intercept by setting x equal to 0. And when x equals 0, y equals 9. We get the x-intercept by setting y equal to 0, and we get then a quadratic equation to solve x squared plus 6x plus 9 equals 0. This quadratic equation can be solved by factoring. There are two numbers which multiply to 9 and add to 6, and they, of course, are 3 and 3, giving us x squared plus 6x plus 9. Now, since we have just x plus 3 squared equals 0, when we set the factors equal to 0, we get x equals minus 3, x equals minus 3. In other words, only one solution. Only one real solution in this case, x equals minus 3. This is the case where the parabola has one x-intercept. So we have the y-intercept, we have the x-intercept. Let's now find the coordinates of the vertex. X is equal to minus b over 2a, and then you substitute to get y. From over here, matching this to y equals ax squared plus bx plus c, a is equal to 1, b equals 6, c equals 9. So x equals minus b over 2a. Substituting, we get minus 6 over 2 times 1, or minus 3. And when you substitute this into the original equation, you get minus 3 squared plus 6 times minus 3 plus 9. 9 plus 9, that's 18, minus 18, 0, which is not too surprising since we already know when x equals minus 3, y equals 0 from the x-intercept. So it turns out the vertex is the x-intercept. Whenever you, for example, don't have an x-intercept, or the vertex and the x-intercept turn out to be the same point, and when you have less than, all the information, in other words, one part doing double duty, we need an extra point, say, to get a good picture of the parabola. Now, let's see what we have so far. We have 0, 9 is the y-intercept here. 9 is the y-intercept. The curve goes through 0, 9. Minus 3, 0 is the x-intercept and also the vertex of the parabola. Okay, so we assume that the parabola is going to be coming down and going back up. It would be helpful to have another point on the parabola. And following the procedure that we used in the last lesson, we will get another point by setting y equal to the constant here, y equal 9. and figuring out what x is. If y equals 9, we get 9 is equal to x squared plus 6x plus 9, subtracting 9 from both sides. 0 is equal to x squared plus 6x. 0 is equal to x times x plus 6. It's very easy to factor. And we get two solutions here. X equals 0, x equals minus 6. Okay, both of these have y values of 9 associated with them. Now 0, 9, we've already plotted. This now gives us another point, minus 6, 9. 1, 2, 3, 4, 5, 6. Minus 6, 9 is another point on the parabola. We now know enough to get a fairly decent sketch of the parabola. And we recommend doing something like this whenever, as I said, the vertex turns out to be equal to the x-intercept, or you don't have x-intercepts, when you have less than all of this different information. Okay, and you feel your parabola can use another point. This is a convenient one to get. Okay, the last thing I want to do on this tape is to mention that there are other equations of parabolas. I gave you one. I said the graph of an equation of this form, where a, b, and c are constants, okay, and a was not equal to 0, is a parabola. That is true. There are also other equations which represent parabolas. So let me just end with a little note here. The graph of an equation of the form x equals ay squared plus by plus c equals 0, where a, b, and c are constants, a not equal to 0 is also called a parabola. And I'd like to just sketch one of these to give you a feel for it. Okay, so it doesn't have to be in this form, y equals ax squared plus bx plus c. You could have a parabola in this form. Okay, the graph of an equation of the form x equals ay squared plus by plus c equals 0. Once again, a, b, and c are constants. A is not equal to 0 is also called a parabola. Now, while graphs of parabolas of this form, okay, either open, say, up or down, parabolas in the form x equals ay squared plus by plus c either open right or left. Let me give you an illustration. Let's say we have x equals 4 minus y squared. Well, x equals y squared minus 4. We can do it that way. X equals y squared minus 4. We recognize it of the form x equals ay squared plus by plus c. In this case, a equals 1, b equals 0. Since we don't have any y terms, c is equal to minus 4. Okay, we still get most of the information from the intercepts. If we want to find the x-intercept, we set y equal to 0, and we get, if y equals 0, x equals minus 4. When we want to find the y-intercepts, we set x equal to 0, and this gives rise to a quadratic equation. 0 equals y squared minus 4, or in this case, y squared equals 4, y equals plus or minus the square root of 4 plus and minus 2. Okay, so let's see what we have. We have minus 4, 0 is the x-intercept. 0, 2, that's one y-intercept. 0, minus 2, here we have the other y-intercept. Furthermore, it can be shown that the y-coordinate of the vertex is located at minus b over 2a, and the x-coordinate is found by then substituting into the original equation. See, everything is just reversed here. The x's and the y's have been interchanged. So you find the y-coordinate of the vertex by substituting into minus b over 2a. Minus b over 2a in this case would come out to be 0 over 2, which is 0, because b is 0. And then substituting in, when y is equal to 0, x, of course, is equal to minus 4. So it turns out that this x-intercept here is also the vertex of the parabola. And this parabola goes something like that. In this case, the vertex is once again the turning point. In this case, it's the point farthest to the left on the parabola. Okay, and that brings us to the end of this tape.